Simple machines. A simple machine is a mechanical device used to manipulate forces. We will be manipulating the size, the direction, or the distance of an applied force. And since they manipulate forces, they affect how work gets done, how energy gets transferred. But one thing to keep in mind is that they do not create or destroy energy. You cannot do that. The law of conservation of energy still applies. So all the simple machine will be doing is transferring energy from one object to another, or manipulating how work is done. Now we will focus on three simple machines that you probably studied in 8th grade. There are other simple machines that are either a version of these three or a combination of these three, in which case we call them compound machines. But levers, some example of levers are basically building materials or building tools like hammers, screwdrivers, pliers, crowbars, and so on, but also sporting equipment like baseball bats, tennis rackets, golf clubs. Those are all examples of levers. We'll talk about those as we go along here. And then we have pulleys, and I'll give you some examples in class of these things, and inclined planes or ramps. Now, one of the big concepts with simple machines is what we call a mechanical advantage. It's the quote-unquote force multiplier. There is the ideal or theoretical mechanical advantage, which we will call IMA or TMA. These will reference the situation where we have no friction. Then we have the actual mechanical advantage, the AMA, which accounts for friction. The AMA will always be less than or equal to the IMA. When there's no friction, the AMA equals the IMA. The efficiency, E, is the effectiveness with which energy is transferred. When there's greater friction, there's less efficiency. When there's no friction, the efficiency, E, is 100%. So let's give you the definitions mathematically and then some examples. The IMA or TMA is the distance input over the distance output. D stands for distance. Distance over distance. I'll give you an example in a second, but since it's a distance over a distance measured in meters, what's going to happen here is that the units will cancel out and the IMA, TMA will have no units. Essentially, that's going to happen in all four cases here. There'll be no units for these concepts. The AMA is the output force, the force out, over the force input. That says force out over force in. That's out. So, generically speaking, however, the force output will be your load or your weight that you're trying to lift with your simple machine. And the input force will be your effort, the force you're applying to lift your load. And once again, it'll be a force in newtons over another force in newtons, so the units will cancel out. Efficiency can be calculated two ways. You can either do it by dividing your AMA, your actual mechanical advantage, by your IMA or TMA. Or you can calculate your efficiency by taking the work output divided by the work input. W here stands for work. So we have your work output, which also can be looked at as your energy gain. Your energy gain over your work input. So this is your work input. I'll give you an example in a second. But one more thing I would like to define as we're going along here is power. Power is equal to your energy or work divided by the time. Your work or energy divided by the time. Symbolically, it's either W over T, that's your power, or it's your energy over T, T standing for time. So the units for power are either your energy units or work units, which are the same, which are joules per second. Those are the units for power, a joule per second. And we call a joule per second, we call that a watt. It could get a little confusing here because the abbreviation for watt is W, so we have to be very careful because work is also abbreviated with a capital W. You may have heard of a horsepower. 1 horsepower is 746 watts. The horsepower is an English unit derived from back when they used horses to do work. So 1 horsepower was symbolic of what 1 horse could do in a given unit of time as compared to our machines like your steam engines and so forth. So here's an actual example. Here's a sample pulley system like we looked at in class. We have 2 pulleys. The black circles are pulleys. We have a fixed pulley attached to a ceiling bracket, and the bottom pulley attached to a weight, or a weight is attached to the bottom pulley, and the red string or rope is wound around these 2 pulleys. Now, we need to find the AMA, or actually the IMA in Part A, and with pulley systems you can take a shortcut. You simply count the number of segments of rope that are wrapped around the bottom pulley. In this case, you have 2 pieces of rope, 2 segments of rope that I'm kind of indicating slightly here on the bottom left. 2 segments of rope that are attached to that bottom pulley. I've used 2 little black marks there in the diagram. I'll point towards them. So the ideal mechanical advantage here, the IMA is simply 2, just counting the 2 segments of rope. Part B, we have to calculate then actually the AMA. The AMA, if you look at the previous page, is the force output divided by the force input. The AMA here is, once again, the force output is what you're lifting, your load. In this case, it's 1,200 newtons, divided by your input, or your effort, 700 newtons. The newtons will cancel out, and the AMA here comes out to be 1.7. Ideally here, it should be 2. You should be using half the weight. In other words, half of 1,200 is 600 newtons. You should be able to lift this load with a 600 Newton force. But because of friction, friction must be accounting for the other extra 100 newtons of force necessary to pull or lift this particular load. Or the pulleys themselves have weight and there's friction, the rope has some weight. But the actual mechanical advantage here is 1.7. Now in Part C, we need to come up with the efficiency. Well, the easiest way to get the efficiency here is to use the first equation. If you look on the top of the page or the other page, it's the AMA divided by the IMA. In this case, E is 1.7 divided by 2.0. It comes out to be, in decimal form, 0.85. You multiply by 100, the efficiency is 85%. Alright, now Part D, how much rope do you need to pull? You can do this by the IMA equation. The IMA equals the distance input divided by the distance output. In this case, we already know the IMA is 2. We want to find how much input distance we need. The output is how high we need to lift. It's been shown here at the top. It's 3 meters. We need to lift this thing 3 meters. So to find our input distance, let's just take 2 times 3. The distance input will be 6 meters. In other words, because the ideal mechanical advantage here is 2, you're going to be using half the force in the ideal case, 600 newtons, but in this case 700 newtons, to lift this load, but you can only lift the load half as far as you're pulling the rope. You're pulling the rope 6 meters to lift the load only 3 meters. So that's your input distance. Here we have a piano that we're pushing up a ramp. It's a long ramp. My diagram is not to scale. Because I cannot lift this piano, it's a very heavy piano, it's 1,450 newtons, but I'm going to push it with a force of 180 newtons. My objective is to lift it off the ground onto, say, a truck 1.2 meters high. So the ramp helps me do this work. It's lessening the force I need, but it's increasing the distance. So in part A here, I need to figure out the AMA. The AMA is the force output, or the weight, divided by the force input, my effort. The AMA here, I'm lifting or pushing a 1,450 Newton piano with a force of 180 newtons. The AMA comes out to be here 8.1. I'm pushing something that's 8.1 times heavier than my effort. So that's my AMA. Part B. To figure out the efficiency, I want to figure out the IMA. The IMA will be my distance input over my distance output, if you look at the equation. So the IMA here, my input distance, I have to push 14 meters. The net result is I'm lifting this thing 1.2 meters. Your output distance is almost always how high the weight goes vertically. So the IMA here is 11.7. 11.7, that's the IMA, or TMA, theoretical or ideal mechanical advantage. That's actually not my answer, though, because I want the efficiency. And the efficiency is the AMA over the IMA. Since we have both of those now, the efficiency is the 8.1 divided by the 11.7. So the efficiency comes out to be 0.69, which we convert by multiplying by 100 to get the percent. It comes out to be 69% efficient. If there was no friction, it would be 100% efficient. Part C. Let me switch to blue. Part C, the work input. Well, work, as we've learned, is your force times your distance as long as they're in the same direction. In this case, yes, your force, the work that you're doing, the input work that you're doing, is you're applying a 180 Newton force, and it's moving 14 meters up the ramp in the same direction you're pushing. So your work input is 180 times 14, which is 2,520 joules of work input. And finally, we have to figure out the power that you supplied. I'll switch to another color. Power is your work or your energy over the time. Well, the work you did was 2,520 joules. The time is 2 minutes, but that's 120 seconds. You want seconds. So you have that many joules and that many seconds. That comes out in joules per second, or watts. If you do the calculation there, the power comes out to be 21 watts, which is good enough. If you want to convert to horsepower, you would divide by 746 to get that in horsepower if you wanted to use English units. If you do the conversion here, that comes out to be 0.028 horsepower. That's an extra calculation if you want to do that. In summary, simple machines are devices that help us manipulate forces to do work, but they do not do the work for us. We still have to do the same amount of work. For example, we could have a moderate force over a moderate distance to do a certain amount of work. In all three cases here, the same amount of work is done. Or like we saw in the two examples, like moving the piano with a small force but a large distance, 14 meters, helped us do the work of getting the piano up a ramp and on top of a truck 1.2 meters high. That's what we're doing most of the time with our examples, small forces over large distances. Or you could have a large force over a small distance. That's usually the case when you're using like a baseball bat or a tennis racket or a golf club. You're applying large forces over a small distance to get some work done. But simple machines manipulate forces, but they do not do the work for us. Sorry, we still have to do the work ourselves.